Hello and welcome back. We're going to continue with the plate girder. Take a look what I have on the board for the problem. We have this built-up girder, which is made of the 3/8 by 82 inch plate for the web, and for a flange we have a 20 inch by 188, and it's a FY36 steel. We're going to design this beam, this girder, find out if we need any stiffener and where we need the stiffeners. So let's say we have the 100-foot simply supported beam. Dead load is 1.1 kip foot, not including the weight of the beam. And then live load is 22 kip per foot. Because the beam is so massive, we really got to include the weight of the beam itself. So let's go ahead. We know the size of the beam, so it's easily calculate the weight of the beam itself. So we know the area is going to be equal. We're going to have two of these. It's 1/8 by 20, 1 and 1/8 times 20 inch, and let's divide that by 144, and then we have the web, which is a plus 3/8 times 82, and divide that by 144. Let's multiply the whole thing by the steel weighs 490 pounds per cubic foot. So the weight's going to come out to, that's the area. Let's make that the weight of the beam. And that comes out to 258 pounds per foot. Okay, so let's calculate the load both in ASD and load resistant factor design. So it's going to be WU equal 1.2 times, we have 1.1 plus 250, that'd be 1.1 and 1.35, that's including the beam weight, plus 1.6 times 2, and WU comes out to, that's a 5/8, and so that comes out to 4.83 kip per foot. And allowable stress design WA comes out to 1.358 plus 2 is 3.358 kip per foot. Now we want to know what the reaction is right here for both of these two. And of course, you know that that is basically your V right here comes out to WL divided by 2 because it's uniform distributed loaded. So therefore, we're going to say RU is equal V, which is equal WL divided by 2. W is 4.83 times 100 divided by 2. That's L divided by 2. And that comes out to 241.5 kip. Same thing here, WL divided by 2 is going to be 3.358 times 100 divided by 2, and that is 167.9 kip. So in order for us to find out whether we need a transverse stiffener or not, there has to be two conditions we got to satisfy. Take a look what we have on the board, and that is from section G2.1 in section 3. It says transverse stiffeners are not required where H over T W is less than 2.46 square root of E divided by FY. Let's see if we're going to meet that satisfaction. First, we're going to find out what's H divided by TW. So we have H divided by TW, that equal 82, and the 3/8 is 0.375. That comes out 219. And the spec says if it's less than, less than 2.46 square root of E divided by FOI. And this comes out to 2.46 time 29,000 divided by 36, which comes out to 219. Is it less than 69.82? It's not. Therefore, if this is not less than that, obviously it's bigger, and that means we need to require stiffeners. So condition 1 is satisfied. However, we got to continue with the equation shown on a section G2. Okay, so since this came out bigger, we say yes to stiffeners. Stiffener for this plate girder, 2 conditions has to be met. 1 condition was based on a spec, met. The second condition, we got to find the shear capacity of this plate girder. If that shear capacity is less than a shear, applied shear by the load, that means it's going to fail. So we got to have stiffener to it to make it work. And so basically, what we're saying, if to this pre-accept, if via n is less than VU, then yes, stiffener is required. But let's find out. I'm going to go ahead and erase the board so we can start, see if we're going to meet the second criteria. So far, so first, when we tried out, we found out this H over TW came out more than this, and therefore, based on that, we require stiffeners. And the second, and then because of that, then the KV comes out to 5.34. Take a look at the spec. So now condition number 2, criteria number 2, got to be satisfied in order for us to say we need stiffeners. That means the shear capacity of this, basically the web, should be less than capacity, less than the applied load, the shear due to applied load. That means this is not strong enough to handle this shear, and therefore we're going to put stiffener to it. So this got to be satisfied. And equation for Vn, that should be Vn. The equation for Vn is 0.6 Fy AW CV1. So what is CV1? Again, per spec CV1, if H over TW is less than this, then CV1 is equal 1. But if it's more than that, then we have to calculate CV1 using the formula on a spec. And in our case, 219 is more than 72, so it's bigger. Therefore, we got to calculate CV1. And the formula for that one is CV1 is equal 1.10 square root of KV E divided by FOI, divide the whole thing by H over TW. So which comes out to be 1.1 square root of KV came out to be, we said it was 534 time square root of 29,000 KSine divided by FY was 36, and divide the whole thing by H over TW is 219. And CV1 comes out 0.329. And now I'm going to calculate Vn based on that. So Vn is equal calculate Vn now, which is a 0.6. FOI is a 36. AW is the D. So let me write down here. AW, it's D times TW, and D is 82 plus 1 and 1A. W makes it 84 and a quarter, 84.25. So that's going to be 84.25 times TW is a 38, and that comes out to 31.59. So I'm going to come back and say 0.6 times 36 times 31.59, and what else we have? AWCV1. CV1 came out to be 0.329, and that comes out 224.5 kip. So now we're going to take this and apply the resistance factor and safety factor to it, find out if it's going to be more or less than the shear capacity due to applied load. Okay, so here we're going to have a phi time Vn, and that's going to be equal 0.9 multiplied by 224.5, which comes out to 202.1 kip. Now, this is the capacity, shear capacity of this beam, and we can see is less than 245. So 202.1 is less than 241.5. Yes, we need stiffeners. So yes, we need stiffeners because that's less than that. So we can go ahead and do the same exact thing over here, which is going to be this divided by omega. So we're going to say Vn divided by omega is equal to 224.5 divided by 1.67. That is 134.4 kip, which is less than 167.9. Yes, we do require put the stiffeners. So now we know we need stiffeners. We're going to move into the next stage. Let me erase this. We come back to it. Okay, so now we're going to go ahead and work on stiffeners. We just take a look what I have in the picture. We want to know what is the distance between the stiffeners. If you, the example in the textbook, you're going to see probably they're going to say, okay, use A is equal 100. But how would you get to that? And they say using trial and error. Experienced designer have a good idea. Usually they say, okay, the spec call for aspect ratio, which is basically A over H, has to be less than 3. But again, depending on how much design you've done and how experienced you are, you know probably 1.2 to 1.5 is a good number, and or 1 to 5, 1.25, 1 to 1.5 might be a good number depending on the situation. And you can find out, okay, I can find what my A is. But let's go ahead and we're going to work backward to find out what is the spacing that we require. What are we doing here? You look at it that the load that we have is 241.5, the shear that we want to beat. Because the reason we need a stiffeners because this is higher than capacity, the shear capacity of this beam. So now let's look at, we're going to look for a shear capacity. We want to have a shear capacity be bigger than that. How much? Let's make it about between 250, 55. We don't want to be too close to it. So we want to say we want our phi Vn be bigger than 241.5. Okay, not a problem. So now we have that. So what number should we have here to be bigger than 241.5? Well, I'm going to say how about 250 to 260. That's bigger than 245. Let's say 255. Okay, 255 we want, which is bigger than 241. That means phi times Vn is equal to 255. I'm going to go ahead and say, okay, phi times Vn is equal to 255. Therefore, Vn comes out to 255 divided by 0.9 and 283. All right. Now, going back to the formula, we know Vn is equal 0.6 Fy times AW times CV1. We know this already calculated from the previous step. We know this, we know this. We don't know this, and we think this should be that number, so we're going to figure out what CV1 is going to be. So if I'm going to say, okay, 283 is equal 0.6 times 36 times AW came out to, I forgot what I wrote down, 3159. 31.59 times CV1. So that will give me CV1 equal 0.415, okay? That's fine. We know CV1 equation is, it's on a board that we have 1.1 square root of kV time E divided by FOI divided by H time H divided by TW. So we know everything except for kV. And we're going to say CV1 came out to 0.415 equal 1.1 square root of kV time 29,000 divided by 36, and divide the whole thing by H over TW came out to 219. So now we're going to find out what is kV it's going to be to satisfy to 0.415. One way you can do it, put this in Excel and just go ahead and come up with the so I'm going to refine this equation right here, and I end up with 82.6 equal square root of 805.5 kV. And then I'm going to go ahead and make myself a chart right here. Say, okay, this is kV, and what is it going to give me for that number? So I'm going to start from 1, and then 1 going to give me 28. That's not even close. And then I'm going to go to 4. 4 going to give me 56. That's not close. You can use the Excel sheet, pick them up in 2 seconds. I'm going to go for 8. 8's going to give me 80.2. That's pretty close. And then what if I use like 8.4? And 8.4, we can refine it, make it a little bit closer. And 8.5 finally going to give you the better chance if you make this to a 8.5. And you're going to get 82.6. But anyway, now, so we know the kV we're looking for to come out to that, kV is equal 8.5. So now we know here, and we're going to find out kV. You can use trial and error, just put different numbers, see what you're going to get. Or you can just put in the formula in Excel and figure it out. It comes out to 8.5. Great. So now we have that. The next step we're going to go ahead and try is, we know kV is equal 5 plus 5 divided by A over H squared. Okay, so we know this is gonna, we're looking for this becoming an 8.5 to work out for our number. So I'm gonna go ahead and say 8.5 equal 5 plus 5 divided by A over H squared, A over H squared. If we simplify this, put 1 here and make a cross multiplication, got to be careful, this 5 is right here. If we make a cross multiplication, bring 5 over here, they become 3.5. So I get 3.5, that become 3.5 divided by 5. And then I will have 1 over A over H squared. And if I go ahead and further multiply, H is 82. So let's plug that in. That become A over 82 squared. And that become 1.42. And even further simplifying it, it become A over 82 is equal 1.2, and therefore my A is come out close to 100. So that's how we guess at what A is going to come out. An experienced designer doesn't go through all this stuff. It goes into 100 right away. It says, okay, the aspect ratio A over H I'm looking for maybe should be between 1 and 1.5, and it's going to use 1.1, and then it's going to use the spacing A is equal 100, and then going to come back, see if it's going to work. So if you look at a textbook example, stuff like that, they go, let's use A is equal 100 based on trial or error, but they don't say how they got it, and this is how you can get it if you're not experienced. So I'm going to erase this board, and we're going to use A over A is equal 100, and we're going to continue. We're going to go ahead and assume A is equal 100. That's a very educated guess that we just did, 100 inch. And therefore, based on that, our KV comes out to 5 plus 5 divided by A over H squared, which is come out to 5 plus 5 divided by 100 over 82 square. That's not a good looking square there. And therefore KV, in this case, if you plug that in, 8.36. And now we have KV, we can calculate CV, which is equal 1.1 square root of KV times FOY divided, no, E. E divided by FOY, and the whole thing divided by H over TW. Now we have 1.1 square root of 8.36 times 29,000 divided by 36. The whole thing divided by 219. So CV is equal 0.412. Now we can go ahead and calculate VN. And VN comes out to 0.6 FY AW CV1. We have all these numbers. 0.636. AW came out to 31.59 times 0.412, and VN comes out to 281 point kip. That's why we guessed at this first to say, okay, this is a good number. And now we're going to go ahead and take this over here, and we're going to say, okay, we got this phi times VN, which is equal 0.9 times 281. 0.1 is equal 253 kip, which is bigger than that, and that's good. And if I can do the same thing over here, it's going to be Vn divided by omega, which was 281.1 divided by 1.67, and that's equal 168.3, which is bigger than 167.9. So this checks out, and this checks out. If we put a stiffener in away from the support system, put 1/100 inch away, then we can say, okay, it's going to increase the shear capacity of this girder. So let's continue with this. I'm going to erase this for a minute. So we said we're going to put our first stiffener in 100 inch away from the support. So now we put this stiffener in 100 inch away. We're going to go ahead and calculate the shear stress. We're going to say, take this beam right here. We came in 100 inch away from the reaction, which was right here. And our reaction, which was the maximum shear, came out to 241 point kips, which is the reaction, which is the maximum shear. And that's how we calculated, based on using load resistant factor design. And our load is 480.83 kip per foot, which we did calculate it. So now if I come in 100 inch away, I'm going to put a stiffener in here. So I'm going to make a cut right here. All the structural analysis you did before got to come in handy here. So cut the beam, and you cut the beam, we want to find out what is the shear capacity here. So let's calculate this shear. Basically, if we do summation FOY is equal 0, remember that in the kindergarten when you learned that, equals 0, going up is positive. I'm going to have 241.5 minus, make this to a vertical force, so it's going to be 4.83 times 100 inch. That's a per foot. Be careful. So I got to divide this by 12, and that will give me the shear force right here in the middle, and plus this one, so it's going to become equal 201.3 kip. So now our shear capacity here is at 201.3 kip. So this was in load resistance factor design, and for ASD it's going to be basically our shear capacity came out to 167.9 minus, and our W is 3.358. 3.358 times 100 divided by 12, and that comes out to 139.9 kip. I'm going to write it here. Let me erase this here. Okay, so now this is the shear capacity 100 inch away, not the shear capacity, the shear based on applied load 100 inch away from the support. And hopefully this is less than the shear capacity of the girder. So we're going to say, okay, this is come out to 201.3, 201.3, which is less than 202.1 kip, way too close. I don't like that. This one comes out to 139, which is we call this, let me write this down correctly. This is basically a VU is equal. And this one is a VA, 100 inch away at 139.9, which is more than 134. That's no good. This one makes it just by a hair. So that means in LFRD you can get away, just put one stiffener here, 100 inch away. But in allowable stress design, you really got to go ahead and put a second stiffener in. And when you have a stiffener here, we're going to have something called tension field, which we can use that. And I have an explanation for that on the board. Take a look at it. Remember, we said the spec called for A over H should be less than 3. What if we say A over H is equal to 3, and therefore we know this is 82, so A divided by 82 is equal to 3, and let's use the A of 3 times 82 is 246 inch. So we're going to put another stiffener away down here. You keep going here, and put another one here at 246 inch away. And now we have to calculate KV, which we've done before. KV is equal 5 plus 5 divided by A over H squared. So it comes out, which is equal 5 divided by, 5 plus 5 divided by A is 246 divided by 82 squared, and that comes out to 5.56. And out here, based on the formula, that our H divided by TW, which is 219, is it bigger or smaller than 1.37 times square root of KVE divided by FOY. And if you plug that number in, that become 1.37, let me write it down, 1.37 times square root of 5.56 times 29,000 divided by 36. And that comes out to 219 is bigger than 91.7. So because of that, then we can go ahead and calculate CV from equation G211, which is on the board. CV2 comes out to 1.51 kV times E divided by H divided by TW square times FY. And it comes out to 1.51 kV came out to 556 and 29,000 KSI. Divide the whole thing by H over TW came out to 219 square times 36. So that gave us CV2 as 0.141. Came out to 1.41. Let me erase this. So I'm going to write here CV2 came out to 1.41. And I'm going to erase the rest of that stuff up here. Note I have on the board. Let me read it. It says when 2 times AW divided by AFC plus AFT less than 2.5 and H over BFC less than 6 and H, then Vn is equal to that. So let's go ahead and figure that out, see if you can get that working. Therefore, I have 2 times AW and divided by the area of the flange and compression plus the area of the flange and tension, which is equal 2 times, we had this came out to 31.5 before, 31.59, okay, divided by 2 times area of the flange and tension, which is right here, area of the flange in, sorry, I take it back, area of the flange and compression, area of the flange and tension, which they're both basically equal. So there's 2 times, they both equal, which is 1 1/8 times 20 inch. So that become 1 1/8 become 1.125, 1.125 times 20 inch. And that comes out to 1.4, which is less than 2.5. And we satisfied that condition over here. So now we're going to go ahead and the other 2 conditions, we can satisfy those 2. And which they were H divided by B of FC, and that comes out to 82 divided by FC the B of the flange and compression, which is right here, and that's 20 inches. 20 inches, and that comes out to 4.1, which is less than 6. We satisfy that. Same thing, H divided by B of FSC, FT, take it back, which is 82 divided by 20 again, which is 4.1, less than 6. We good, we good, and we good. Therefore, based on that, I can say my Vn is equal 0.6 FOY time AW time CV2 plus 1 minus CV2 divided by 1.15 times 1 plus A over H squared. So I'm going to plug all those numbers. We have all those numbers. So Vn is equal 0.6 times 36 times 31.59 times I came out to the CV2. I think that's wrong. That's a 0.141. So 0.141 and plus 1 minus 0.141 divided by 1.15 times square root of 1 plus A over H became 246 divided by 82 squared, become 257.4 kip. So this is our capacity of a VN after we put the second stiffener in. You notice that the first stiffener was almost satisfactory at for the load resistance factor design, and obviously this going to be satisfactory because it's going to be VN divided by omega, which is 257.4 divided by 1.67 comes out to 154.1, which is more than. So that become 154.1, which is bigger than our VA, which is due to the load at 100 inch away, which we are good. Bigger than 139.9, we good. This is how we know if you have a plate girder whether we need a stiffeners or not. It's based on a shear capacity of this plate girder, and then we put a stiffener in it and we run the calculation, and after we put a stiffener in it, the capacity of this shear in this plate girder came out more than the applied load. We went at 100 inch and so on. And hopefully this was helpful. If it was helpful, give me a thumbs up. And if I get a lot of people watching this and they want it, in the next series I will design the stiffeners. If not, but this is good. Thank you.